Hi guys, Miss O'Connell here. We're gonna pick up with example number 16, which is on page 7 of the guided notes document in classroom. Okay, so in 16 we have a 5 kilogram box that slides 4 meters across the floor before coming to rest. We want to figure out the coefficient of friction between the floor and the box, and we're told that the initial velocity of the object is 3 meters per second. So in this type of example, you might be thinking, okay, so if I have the displacement, I have the initial speed of the box, and I have the final speed of the box. Okay, why is this in the work and energy unit? And the reason being is because besides using forces or kinematics, you can also use work in this case to solve this problem. You're not given the time in which the object slows to rest, so it would be very difficult to use Newton's second law in this case, or even kinematics. So because you lack the amount of variables that we need to use work to solve this problem. So I'm going to quickly sketch over here our situation, what we're dealing with. Okay, so on a flat horizontal surface, we have a 5 kilogram box. Okay, that box itself is going to slide 4 meters across the ground. Before coming to a rest. Okay, so the final velocity here is 0. The initial velocity is 3 meters per second. We know the mass of the object is 5 kilograms. We're looking for the coefficient of friction. Okay, so if we're looking for the coefficient of friction, that would mean here that we have a frictional force. So acting on our object here, we have the force due to friction. Okay, if it's sliding, we're going to be dealing with kinetic friction. In this case, it doesn't technically matter what type. We'll have the force of the surface supporting the object, the normal force, and then we'll have the force of gravity as well. Okay, so once the object is technically released, if it's sliding and it's slowing down, if it's sliding and slowing down, the acceleration is going to be negative. Okay, meaning the net force has to be in the opposite direction. So the only force technically acting on this object is the force of friction. Okay, so that force is going to cause the acceleration. It also causes the change in energy of the object. Okay, so in this case, the total work done, total work is equal to the change in kinetic energy. Okay, we know that technically the work done here is by this force, this frictional force. So work done by friction is the total work. And the work done by friction, we know that work is the dot product of the force times the displacement times the cosine of theta. Right, our dot product, I'm going to write the equation up here, work is the magnitude of the force times the displacement times the cosine of the angle between the two vectors. Okay, so our force here is the force of friction. Our displacement is 4 meters. The angle between my displacement and the vector, if we were to redraw this, I'm going to redraw it up here in the top right corner. So the displacement is in the positive x direction. The force of friction vector is in the negative x direction, so the angle between them is 180 degrees. So the dot product of those two vectors is the force of friction times 4 times the cosine of 180. Okay, and in this case, that's equal to the total work. So I'm going to plug that right into my equation. Okay, so in this case, the work done by friction is the total work. The work done by friction is the force of friction times 4 meters times the cosine of 180. Cosine of 180, we get negative 1. Okay, and that will be equal to the change in kinetic energy. The change in kinetic energy, we have 1/2 m times v final squared plus 1/2 times v initial squared. Sorry, 1/2 times m times v initial squared. There we go. Because the object the object finally ends by coming to rest, the final velocity is 0. This whole quantity here, 1/2 times mass times 0 squared, this whole segment here is going to become a 0. Okay, so I'm going to simplify. I don't know what force of friction is, so I'm going to keep that a variable. So I have force of friction times negative 4 meters is equal to 1/2 times 5 kilograms, which is the mass of our object, times 3 meters per second squared. And we're going to solve for the frictional force. So 3 squared, you get 9. 9 times 5, we get 45. Half of 45, we get 22.5. Our units are technically joules because we have kilograms times meters squared over seconds squared. That's equivalent to a joule, so we get joules. 22.5 joules is equal to force of friction times negative 4. We're going to divide both sides by negative 4 to get the force of friction alone. And we get 5.625 newtons, and that's negative. Okay, the force of friction is negative because it's pointing to the left, right? That force is taking energy out of the system. We are not, however, done because you're looking for the coefficient of friction here. We're looking for mu. Okay, we know that the force of friction is equal to mu times the normal force. In this case, right, because it's on a flat horizontal surface, the normal force is equal to the force of gravity, which is m times j. Okay, again, this negative sign only denotes direction for a force. So we're going to not include it when we're solving for mu. Mu can't be negative. So I'm going to plug in for the force of friction. I have 5.625 newtons is equal to mu, which is the coefficient of friction, what we're looking for, times our normal force, which in this case is mass, which is 4 kilograms, times, we're going to estimate G to be 10, so we get 40 newtons is our normal force, or sorry, 50. 5, the mass is 5, not 4. 5 times estimate of G is 10. 5 times 10, we get 50 newtons. So divide both sides by 50 newtons. The units cancel. We're left with a unitless constant, which is what we're looking for. And we find mu to be 0.11, so something very small. So the coefficient of friction here is 0.11. Okay, again, the reason why we need to use work here is because we do not have enough information to use kinematics or Newton's laws to solve this problem. So we have to use the fact that the total work is equal to the change in kinetic energy of the system. Okay, and the only force doing work in this case is the force of friction. Okay, we can use the force of friction or work to find the force of friction, and then what we know about friction to find the coefficient. Okay, so let's take a look at example number 9. This one's a conceptual one. Okay, in example number 9, we have a car. You're driving a car and you slam on the brakes and skid a certain distance. If you had been going twice as fast before you slammed on the brakes, what distance would your car have skid? Okay, so this is one of those relational questions. Okay, so what happens to one side of the equation must happen to the other side of the equation. So what we need to figure out, okay, if you slam on the brakes and you're skidding, the displacement that you skid, okay, how is that related to your velocity or your change in velocity? So displacement that you skid and the change in the velocity, how are those two things related? Well, if you think about it, displacement and the change in your velocity are related to each other by the equation that we just looked at, right? The total work is equal to the change in the kinetic energy. So basically, you want to figure out how D changes. In this case, if you think about it, our car here is going to have those same forces acting on it as our previous example. So once the car starts to skid, the force acting on it in the x direction is going to be the force of friction and the force of friction only. In the y direction, we have the normal force and the force of gravity, which are not super relevant here. Okay, so that frictional force is the force. So work done by friction here will be equal to the total work. Okay, the work done by friction is going to be that frictional force times the displacement times the cosine of 180 times the change in the kinetic energy. If you're skidding to a stop, right, when you press on your brakes, you are hopefully skidding to a stop. The final velocity should be equal to 0. So again, just like last time, 1/2 times the mass times the final velocity squared minus 1/2 times the mass times the initial velocity squared that final velocity should be 0, so that portion of the equation will cancel. So what we're trying to figure out is if this initial velocity is now twice as large as initially, we need to figure out how this displacement will change. Okay, so the mass is going to stay constant, and the coefficient of friction is going to stay constant, and the mass of the object is going to stay constant. So that means that the frictional force will remain constant. In this case, because we're on a flat surface, force of friction is mu times the mass times gravity. Mu, m, and g are all constants, so this force is not going to change. So this change in velocity will cause a direct change in the skid distance, or the displacement that results. So if our velocity is doubled, we have 1/2 times the mass times 2 times the initial velocity squared (1/2) times mass, 2 squared is 4, times v initial squared. So if you're moving twice as fast initially, the change in your kinetic energy is going to increase by a factor of 4. If your initial velocity, or the change in your kinetic energy, increases by a factor of 4, that means that this displacement or skid distance is going to increase by a factor of 4 as well. So what happens to one side of the equation has to occur to the other side of the equation. Okay, so immediately here, without knowing, or without doing this little setup here, if you're moving twice as fast, your displacement's not going to decrease. Okay, so we can eliminate basically C and D. It's either 2 times or 4 times as fast. Remember that the initial velocity is squared. So 2 squared is actually increased by a factor of 4. So that means that the skid distance increases by a factor of 4 as well. Okay, so that wraps up our discussion of work of the system. We have one more concept within work to talk about, which is work due to non-conservative forces. So work done by friction. Okay, we'll talk about how non-conservative forces kind of factor in here in our next or our following class. Before we continue on with work due to non-conservative forces, we have a quick discussion about power to address. Okay, so the idea of power is kind of rarely on the AP exam, but it's something short and quick, and it works really well with work. It works really well with work, and forces as well. So it's usually just an add-on, an added benefit. It's most useful when we're talking about electricity. We usually talk about power more within the E&M side of physics compared to the mechanical side, but it's also present in the mechanical side as well. So we're going to apply power here to a few other examples. Power, work, and velocity are directly related and rely on one another. So it's a good spot to work this in. So heading on to page 8 of the guided notes, we're going to discuss quickly about the idea of power. Okay, so the significance of the horse picture here. 1 unit for power is horsepower. Okay, so the idea of power was kind of derived through the idea of horses specifically, a Clydesdale horse pulling objects, applying a force over a distance, over a certain amount of time. Okay, so that idea of horsepower is actually related to the amount of work that a horse can do over a period of time. Okay, so power is the rate at which work is done. Okay, our equation for power is work over time. And the units for power are watts. Which we use a W to represent as that variable. Okay, so the unit for power is watts. One conversion rate in which, okay, you will specifically use in general in physics, not so much on the AP exam will you see this conversion, but horsepower is a common unit that we use, especially for mechanical power. So 1 horsepower is equal to 746 watts. Okay, another equation for power, which we'll get to a little bit later. An example, I think it's 18. We know what work is, right? So if we have this equation here, power equals work over time. We know that work is force times displacement, okay, which we've been using lowercase d for, but it's also commonly known as delta x. So we have force dot displacement times the cosine of the angle divided by time. We can see here, right? Let's highlight this. Displacement over time. Displacement over time. What's that? Velocity. Okay, so another relationship for power in terms of velocity is force times velocity times the cosine of theta. Okay, so if you have the velocity and the force, we can also find power as well. Okay, but power is defined as the rate at which work is done. Okay, so here are two expressions for power. Okay, so example 17, we have a child pulls horizontally on a wagon. So here's our wagon. And our child pulling. With a force of 75 newtons. The wagon itself moves 42 meters. This is not drawn to scale. In 3 minutes. Okay, so I forgot to say this earlier, but the metric unit for time is seconds. We want this in seconds. So we have 180 seconds. So it pulls 42 meters in 180 seconds. What is the power generated by the kid? the child. Well, we know that power is work over time. Work is this applied force, which is 75 newtons, times displacement, which is 42 meters, times cosine. In this case, the displacement and the force are parallel to each other. They're both in the positive x direction. So we have cosine of 0 degrees, which gives us 1, divided by 180 seconds. So we get 3,150 Newton times meters, we get joules. So I have 3,150 joules divided by 180 seconds, and we get 17.5 watts, which we use a capital W to represent. So the child has produced or generated 17.5 watts. Okay. That one's pretty straightforward. Let's head to the next one. Okay. In 18, we have a car needs to generate 75 horsepower in order to maintain a constant velocity. Okay, so first issue here is horsepower. We want watts, not horsepower, for the purpose of our equation. Why? Because dimensional analysis. Okay, we need our units to be in terms of metric units. So we know that 1 horsepower is 746 watts. And we get a whopping 55,950 watts of energy. Okay, so the car needs to generate 55,950 watts of energy to maintain this constant velocity. All right, so I'm going to take a side remark for a second. So obviously, if the car is moving at a constant velocity, that means that the forces are balanced in the x direction. So in the y, right, we have the force of gravity, we have the normal force. For it to move at a constant velocity, we would have to have balanced forces here. Okay, so probably there's some frictional force in here. Okay, or there isn't a frictional force. I guess it depends on whether there is a applied force or not. But what we're saying here is that the forces are balanced, right? The acceleration of the system is 0. Okay, so we know that the velocity here is constant, and it's this value here. We want the magnitude of the total resistive force acting on the car. Okay, which would, in this case, be the force of friction. Okay, because this object is not accelerating, this power generated, okay, the force that is generating this power is overcoming or equal to the force of friction. So we have power. Again, we know power is work over time. Work is force times displacement times the cosine of the angle divided by time. We only know that there's constant velocity. We are not given any other information. So we need to use the version of power that is reliant on velocity, right? Displacement over time is velocity. So the equation we're using here is power is equal to force times velocity times the cosine of theta. So you know that the power generated needs to be 55,950 watts. That'll be equal to force times this velocity, which is 27.3 meters per second, times the cosine Okay, if we're talking about resistive, it's going to be 180, which is going to give us a -1. Okay, which just means that this force is going to be negative. So I divide both sides by 27.3 meters per second. Watts over meters per second, we're going to get newtons. And our force is 20,000, not 20,000, 2,049 newtons. Okay, last example with power. We have, again, a car. This time we're given the mass, 1,500 kilograms, accelerates from 0 to 25 meters per second in 7 seconds. What is the average power delivered by the engine? Okay, so don't get thrown off by the word average. Power is work over time. In this case, we're given the change in the velocity and the time. We're not given force. Okay, so don't panic. We know that work done by, or work by a force is equal to the change in energy. Right? And total work is change in kinetic energy. We're given the change in kinetic energy because we're given the change in the velocity. So we're going to substitute in for work, we're going to have the change in the kinetic energy over time. So we're going to have 1/2 the mass, which is 1,500 kilograms, times the change in the velocity squared. Okay, in this case, it's 25 meters per second squared. Divided by the time, which is 7 seconds. We get 66,964 watts. Okay, so this is the power that is delivered by the engine. Okay, because it causes this change in kinetic energy. So that power is 66,964 watts. Okay, and that's it. We'll start up with non-conservative work next week.